Hello everyone and welcome back to the School of Quantum. Today with the Hidden Quantum Champions about IONQ, nobody less than IONQ. So grab yourself something to drink and let's hop right into it. Here I'm on the website of IONQ. You see quantum is now. Quantum computing has the potential to change the world and IONQ is leading the way. So IONQ is at the moment one of the largest pure play quantum companies that is stock listed. So they've just acquired Oxford Ionics at the point of this video being produced. And yes, they are working in the ion technology. So before we hop into this website, maybe a couple of words on the base technology, because actually a lot of people are also always interested in how it actually works. So IONQ is using ions. These are atoms that have one electron less, so they become electrically charged. So normally you have in an atom, in a very simple model, you have the nucleus, which is consistent out of protons and neutrons. Protons are positively charged particles, neutrons are neutral, as the name suggests. And then you have the electrons, which are somewhere around this nucleus of your atom. And they're moving in different spheres, in different shells, at different energy levels. Like in a very simple picture, they are moving around these orbits around the nucleus. Now, if you take away one electron, for example, by irradiating it away, by drawing it away electrically, whatever, you will end up with something that is an ion. So basically an atom that is lacking an electron and therefore has a net positive charge. Now, what that allows you to do is you can actually manipulate this atom with electric fields. So if you had an electric field, a negative one, it will get attracted to this negative field. And now what this allows you to do is actually to trap this ion, this ionized atom, in a specific location. Basically, you create, similar to like what you could do with a magnet, right? You have these maglev trains that are kind of levitating above the rails. And similar, you can use electric fields to kind of levitate atoms or not in this case, not atoms, but ions in a specific spot. So you basically use a electric field. In that case, it's even a dynamic electric field, and you can basically position one of these ions in a specific spot. Now, if you use a more sophisticated approach, you can do that with multiple of these, and they will kind of queue up in a row. So you have like a one-dimensional system where you have one of these ions sitting right next to each other. This is now very simplified. Technically, this is much more complex because you actually have to use dynamic electric fields. You have to cool the whole system down first. So you have to make sure that you have a perfect vacuum in there. So there's like a lot of auxiliary stuff happening around this. But at the end, you end up with this chain of this one-dimensional chain, more or less, of ions that are sitting right next to each other. Now, how can you actually manipulate them? How can you make quantum operations with them? So what you need is a two-level system, a qubit. Like, for example, if you had a normal spin, you have to spin up, spin down. Now here you also need something like that. So you need kind of a two-level system where you can, let's say, have a base state and you excite this state, this ground state, up to an excited level. And this transition, this has to be unique. So there cannot be another level above which has the same energy distance, because otherwise you cannot differentiate between the base state, the ground state, the first state, the second state. So you have to have a ground state. Let's say your ion is sitting there in the ground state, not doing anything. Now you excite it to this higher state, and then you have to be able to kind of read it out also. So how is this basically being done? Well, this is done in an optical way usually. So what you do is you basically take a laser light, you shine on the atom and on the ion, and what happens is this laser light is shooting light quanta, so photons, onto your atom or onto your ion. And one of them might hit the ion, and if the energy of this photon is exactly the energy that it needs for an electron to jump for one of these electrons in the shell, right? for one of them to jump from one level to the next higher level, for example, if this is exactly the same distance, then you can actually excite an atom with this, or an ion with this, and vice versa. If you, for example, were to read it out, you need these optical transitions where like an electron falls down from an excited state to a lower state and thereby emits light. So you will see that, like, you will not see it because it's like it's a quantum process. It will not emit a lot of photons, but like if you were to see it, you would see that like when it falls down, there's like one little flash coming from one of these ions. That's like more or less the working principle on which this operates. And then since we have all of them in a chain, you can also use vibration modes. So the like mechanical movement of these of this chain of ions to actually couple those to each other, because in order to build quantum operations, you need to be able to create superpositions and entanglement. So not only like superposition you can still do with a single system, but if you want to entangle them, you need multiple of those. So that's why you need to be able to couple them to each other. This can, for example, be achieved via these vibration modes. So you can imagine that you have like, for example, two ions, and they could be vibrating like this. So basically asynchronously, so both of them go out and in at the same time, but they could also be vibrating synchronously like this, for example, right? So they're like different vibration modes, and with these you can encode different types of information. That's more or less how it works. And with that, now let's hop into what IONQ is showing us on their website. So again, quantum is now, start your quantum journey, contact a quantum solution specialist. So here you see some rotating images of different applications. So now we saw a robot, here we see the Earth. So I think these are like different applications that they are targeting. Here it also says like better battery materials for, like, for example, electric cars, improved drug discovery, and so on. So these are like the different use cases, and I guess we will learn more about these as we move on here on their website. So customers, here we see different customers of those. I'm based in Switzerland, so obviously I see Quantum Basel here right away, which is located here in Switzerland. There's also other European players, like for example Airbus, but of course this is very international. You also see Microsoft, Azure, University of Maryland, like academic institutions, Hyundai as a car manufacturer, Google Cloud, Amazon Bracket, and so on, and Daisy as a player from Germany, I think. Then there are also partners. We see NVIDIA here, Accenture as an consulting agency. We see IMEC, which is also an important European player. DARPA is also very well known, Lockheed Martin in the US, Toyota. So they're like also very well renowned partners. And what do we see here? Meet our newest and most powerful quantum computers. So here we see, I guess, the quantum computers that they have. So there's the IONQ Area, the IONQ Forte, the IONQ Forte Enterprise, and the IONQ Tempo. So the IONQ Area is our universally accessible high-performance flagship quantum system. The Forte is our highest performing commercially available quantum system. Then the Forte Enterprise is our rack-mountable on-prem system for production readiness and hybrid workflows with hashtag AQ36 and 36 qubits. And then we also see here the IONQ Tempo, our commercially advantage capable computer for production applications. They are powered by atoms. That's what we talked about before, right? Like trapped ions. Our quantum cores use nature's qubits, atomic ions, identical, perfectly isolated, and naturally quantum ions provide unparalleled performance. Then we see here something about the cloud. So a quantum cloud made for developers. Forget translating your work into yet another quantum SDK. IONQ works with all of the most popular cloud providers, libraries, and tools. You sign in and get to work. So we see here there's like an AWS example, an Azure example, a Circ example, and a Qiskit example that basically show how to make use of these computers with the different cloud providers. And then here also we see the partner clouds, so all of the free hyperscalers, the American ones, are listed here. And then there's also direct access for the partners, I think. So their mission: to build the world's best quantum computers to solve the world's most complex problems, transforming business, society, and the planet for the better. Our company, building in over 25 years of research, we brought quantum computing out to the lab and into the real world. And then, of course, join us, whether you're an expert in your field or a recent graduate. If you love collaborative and challenging work, we encourage you to apply. So harness the world-changing power of quantum computing. Get started on one of our partner clouds in as little as 10 minutes, or contact us to discuss a custom partnership for your business. And then, okay, there's also the way to contact sales. With that, let's quickly see what we have up here. So there's this products tab, which talks about the quantum systems. I guess these are like what we saw before, the different quantum computers. There's some consulting here regarding the applications, some benchmarking, and of course there's a tab also on the cloud. And we see something about the company itself. We see about IONQ, there's a newsroom, investor relations, because they're a stock listed company. They have an investor tab here as well, which they have to provide. And then there's, of course, a way to contact them. Furthermore, there are also additional resources here. So we see the resource center, level up your quantum knowledge. There's events, documentation on how to use the system. I guess there's a quantum glossary, which probably explains the most important terminology. Something about the technology, so probably something that goes a little bit deeper than what I hopped in with at my original explanation. There's something about publications here, system status, and then there's a support tab. Finally, there's a career and a blog page. But for now, let's hop to the products. Let's quickly go through all of the different quantum computers they have. So IONQ quantum computers, that's a comparison here from the different systems that we saw. It starts with Tempo, and hashtag AQ64 IONQ Tempo is expected to be capable of commercial advantage for certain applications. Tempo is designed to have faster gate speeds, mid-circuit measurement, and a 99.9% fidelity, all helping to unlock larger and more complex problem classes and deliver a faster time to solution. So 64, I guess, ions, or let's say qubits, because technically maybe you can also use one of those to encode more than a qubit. Don't know if they do that here, but let's say it wouldn't be impossible, I guess. I'm also not an expert in this though. Then we see here faster gate speeds. This is important because still, even with these ions, there are certain errors, and like the longer you take to actually process the information, the higher is the possibility that an error might accumulate, right? Because it could be that like you have all this cosmic radiation, something is hitting your ions in the chamber, and thereby creating some error. So the faster you operate, the less probable this is going to accumulate. Then you have mid-circuit measurements. I guess they are like for checking stuff in between. They probably become more important as you start to do like things like error correction. So actively correcting away those errors that are happening. And then here it says 99.9% fidelity. The fidelity is a vocabulary that is relevant in the quantum context, as how precise you can actually perform quantum processing steps, I would say. Maybe that's the easiest explanation of that wording here. So this is going to be, I guess, the future flagship system. but for now, these ones are the ones that are available here. So we see the Area, the Forte, and the Forte Enterprise. They're all commercially available already. What you get for sales, as it seems, are the Forte and the Forte Enterprise. They come with these, here it's also explained. So algorithmic qubits, AQ, and then there's physical qubits as in the atoms, right? Because also when you do error correction, you might take multiple of these physical qubits and create an error corrected algorithmic qubit from it. So maybe that's why they're already differentiating between those here. So that's what we see here. Then we see the fidelity for different operations here. And you see they are very, very precise. So that's good. You see the connectivity. That's like when you have a quantum processor and you have these qubits, you actually, in order to really make use of the number of qubits, you need to be able to connect them with each other. Now, in certain systems, like when you, for example, look at these planary chips, the two-dimensional chip layouts, you can only connect the ones directly that are neighboring with each other because of the fact that, like, okay, you have these connectors, these physical connectors in between them, and it's hard to build more connectors than the ones that are neighboring. So oftentimes what you will see is on, for example, superconducting qubits, you will get this pattern that kind of shows you like which qubit is connected to which, and sometimes you only have one qubit connected to the next one. So it's hard to kind of connect one qubit that is on this side of the chip with one that is on this side of the chip, because you will need to go through all of these intermediate qubits in between, which means you have to do additional operations. And as there are errors accumulating, this becomes more and more challenging. So here, this is an advantage because you have these all-to-all connections, which goes via these vibrational modes, right? So you can hook up every single qubit with every other one. Okay, then on top we see here the operating system, which is first gen. The laser system. So here we see the different laser systems that they have, I guess. So there's the acoustic optic modulator and the acousto-optic deflector. And okay, there's error mitigation. Now, this is to be differentiated from error correction. Error mitigation is like a clever way to reduce the error rates, whereas like error correction is an algorithmic, well, both of them can be algorithmic. But like the error correction is really actively correcting out those errors. The mitigation is a clever way to learn how your system works, where it accumulates errors, and then to kind of mitigate those. So it will never, like error mitigation will never get you to this like super sophisticated stage where you can do an infinite amount of operations, but it will get you on an intermediate basis to a, I guess, better result than like using the bare system. Okay, so that's an overview over the different products. Let's quickly look at the tempo because it doesn't say too much on this other page there. So first of all, that's what it probably looks like, which is like a very elegant design, I guess. You can also see it looks a little bit like in a supercomputing center. You see these racks that are sitting next to each other with this silver line here in between. So very interesting design choice. And then you also see these parabolic functions looking like points here on the system. It says a paradigm shifting quantum computer. So here you can get more info about it. And here it now says, okay, we have these algorithmic qubits, which is 64. And then we have the target qubits, which I guess is the physical ones. The number of physical qubits, which is going to be 100. So there's probably going to be some type of either it's like an active error correction happening, or there's like some ancilla qubits or whatever in the system, which are being used to actually do the operations that you want to carry out. So then it says commercial advantage readiness starts today. Tempo is designed to have more available useful computational states than any computer in history. It is estimated that the first movers in the quantum space will capture up to 80% of the commercial value in the quantum marketplace. We believe Tempo's performance and system capabilities will enable new production-ready quantum applications. Quickly on these 80% here. So this is this famous like first mover advantage. I think there's also an interesting book, like I think it's called 0 to 1 from Ray Kurzweil, where he explains this concept, why like moving early actually gives you the advantage, because you can kind of build, maybe you can call it the monopole situation, where you are like the first one to do something and gain a technological advantage. Very interesting read, by the way. Explore other quantum systems. These ones are the ones that are already available. And then, okay, we see here there's like cloud support, and learn about #AQ. Now let's quickly also dive into the applications that they promote here. We see advanced access to the latest IONQ hardware, support from the best research in industry, solutions for every stage of your quantum journey. So there are like different bundles, I guess, which they are offering here. So there's the prepare stage, baseline problem set. There's the build stage, application development, and the expand stage, where you identify new problems. So that's like, I guess, the quantum journey that you go through. So first you take a look at your organization. That's also what it says here. Understand where there's like potential advantage to actually apply those quantum algorithms, to actually look into, for example, optimization problems with quantum computers and so on. So you do this consulting, you create a roadmap of how you move on. Then the next stage will be this development of the actual application, right? So like getting access to a system, integrate this into your existing system, create like algorithms, get this NYSE, so let's say quantum system support for the existing quantum computers, QPUs, and then the next stage will be, okay, let's see how this can be expanded, what other, I guess, applications can be there, and so on. Okay, application areas we see here. This is like our self-driving or electric car again. And here it says computer vision and image recognition, material research, natural language processing, high-tech electronics, pharmaceuticals, human and computer interface, and geo-exploration. There's also something that's like all in the product space. Then we have risk management and finance. There's portfolio balancing and optimization, credit and lending models, procurement risk and analysis, and project sequencing. And then finally, there's supply chain manufacturing and operations. You have supply chain management, package loading optimization, predictive maintenance, shipping and logistics, and fleet management in there as the applications that they're targeting. And then, okay, here you see the team, which is basically, I guess, helping the customers throughout these different stages. And also it says like what expertise they have. Looks like a pretty big team here, but it makes sense because they also have some customers that they are working with already. Here, I guess we see some case example application development process, where it goes through these different stages that we saw before. And then, yeah, you can basically submit something here, and then I guess they will reach out to you and check with you about the application. Let's also quickly see what the benchmark page here says. So I guess optimization, quantum simulation, and quantum machine learning. Here we see the different spaces, energy, logistics, pharmaceutical, finance, and chemistry. And then we see like optimization, quantum simulation, and quantum machine learning. Like, I guess that is to show like which level these three different approaches here can be applied in these different industries. Okay. And then we see here the system. There's some predicting performance against our intended workloads. Okay, so there's like some examples here. And then, here it really explains like how the whole idea works, compare the scale of the computational space. That's a nice comparison. I guess a nice comparison here. Okay, wow, that's interesting. So, quick side note on that, like the space that you're computing in is growing exponentially. So I think technically, if you take a system and you just add another qubit, like just from going from 1 to 2, you're basically doubling. But then also going from, I don't know, 10 to 11, you are again, I think, like doubling. So going from 10 to 16 is 64 times increasing the calculation power or the computational space, which is not necessarily the calculation power, but like the space that you can use to encode and process a certain information, like from a physics point of view, the Hilbert space that you can access with such a machine. And it basically is to show you that like with every single qubit you move quite a bit the needle on the power that such a system has. Okay, and then there's like other explanations here on this. Okay, but I will not go into the details of all of this now. I mean, you can check it out if you're interested in that. Let's quickly also check out the quantum cloud. So we saw before they are working with all the hyperscalers and they also offer their own access. So we see here Google Cloud, AWS, Microsoft Azure, and IONQ themselves. We see the different types of programming environments that they allow access via. There's also some more explanation here. So you have Qiskit, Zerg, CQ, TCAT, Q Sharp, QCW Forge, Project Q, PennyLane, and TensorFlow as ways to access the system and do operations on there. There's also, I guess, this graphical interface here where you can see like the different stages of your algorithm in the graph. It also says there's simulators for this. So I think, before you actually move stuff to the quantum computer and generate costs, it makes sense to start with like easy simulations. But of course, the more you scale up the number of qubits, the harder it becomes to actually do the simulation on your machine, right? And then the IONQ Quantum Cloud helps you get more done. So there are some statements here. Here you can see what, I guess, the different types of access allow you to do. So there's like the simulator access for early exploration. You see that's even like for free. You see that there's like different systems available on different clouds. So you have, for example, the Forte Enterprise, which is only on Amazon Bracket and not on Microsoft Azure and Google Cloud. The Aria is actually available on Azure and Amazon Bracket, but not on Google Cloud. But on Google Cloud, you find the simulator and the NYSE simulator. And the only place where you can access all of it is basically via the direct access if you, I think, go via IONQ right away. There's some more stuff down here. Like, for example, the application and development support, which you get with all of them. There's IONQ Quantum Cloud Console, which you only get with the Google one, I think. And so on and so forth. Like also when it comes to the different programming environments, for example, the Q Sharp is not available in Microsoft Azure and Amazon Bracket, which is kind of surprising that Q Sharp is not that Q Sharp is only working on the Google side of things. But okay, that's interesting to know. And there's even more here, like for these additional programming languages. It seems like Google does not give you access to the actual machine, but it actually gives you access to most of the programming languages, for example, Whereas here with Amazon Bracket, you don't get access to so many different programming environments. That seems to be quite proprietary on Amazon's own one, which is Bracket. But therefore you get like access to the best systems, the largest or quickest systems out there. So there's some differentiation also between them. And if you're interested to use one of them, then I guess it makes sense to look up here. And there's also pricing details about that. And I guess prices will change over time. It's a dynamic thing. Very quickly on the company, so about IONQ, our mission to build the world's best quantum computers to solve the world's most complex problems. Quantum computers are a revolutionizing technology. They have the potential to transform business, society, and the planet for the better. And IONQ is at the forefront of this revolution. After over 25 years of academic research, IONQ was founded in 2015 by Chris Monroe and Young-Sang Kim with $2 million in seed funding from New Enterprise Associates, a license to core technology from the University of Maryland and Duke University, and a goal of taking trapped ion quantum computing out of the lab into the market. In the following 3 years, we raised an addition of $20 million from GV, Amazon Web Services, and NEA, and built two of the world's most accurate quantum computers. In 2019, we raised another $55 million in a round led by Samsung and Mubadala and announced partnerships with Microsoft and Amazon Web Services to make our quantum computers available via the cloud. In 2020 and 2021, we built additional generations of high-performance quantum hardware and added Google Cloud Marketplace to our cloud partner roster and announced a series of collaborations and business partnerships with leading academic and commercial institutions. On October 1st, 2021, IONQ began trading as IONQ on the New York Stock Exchange, making it the world's first public pure-play quantum computing company. We remain hard at work realizing the world-changing potential of quantum computing. And I mean, even since then, it has become it is a very interesting player. It has become actually a topic that is even being discussed in the mainstream, like even in the mainstream financial media. You now read about IONQ, people are talking about it, there's a certain interest about it. And if you are interested in actually like investing or understanding it, like working with it, I think it makes sense to like learn a little bit about the technology behind it, to understand the impact of quantum computation, and then make an informed decision whether it makes sense or not for you to actually invest yourself into that or not. Here we see the leadership team, then there's the board of directors, and I think that's about it for this page. As mentioned before, there's like also newsroom, investor relations, and many, many more resources. I encourage you to check those out if you want to learn more about the company itself. In order to not make this video too long, I will cut it off at this point. I hope you liked it. If so, please give the video a like, and then see you in the next one. As always, stay hydrated and goodbye.